Okay, hello and welcome back to a chemistry talk. Today I'll be starting a discussion on equilibrium. There was a lot of math with equilibrium, but today we're not going to do the math. We're going to talk about a lot of the concepts and mainly about a principle known as Le Chatelier's principle. So first, briefly about what an equilibrium reaction is. Usually you can tell it's an equilibrium by the arrows. You'll either see a double arrow kind of going signaling the forward and the reverse, or you'll see an arrow that has two sides on it. Usually I use the second notation, but you do see it sometimes written like that. So an equilibrium reaction is when the forward reaction, your reaction going to product, is the same as the reverse reaction where your products are going to reactant. An equilibrium state can be physical or chemical depending on the change back and forth that is occurring. The forward reaction is the reaction going from left to right. You're going from reactant to product. The reverse or backwards reaction is going from products to reactants. So Le Chatelier's principle was created by I believe he was French chemist, Henry Louis Le Chatelier, and the chemical definition is if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. Meaning, when you have a reaction that's at equilibrium, it has a perfect amount of concentration on each side where it is in this constant state. If I change, or a chemist changes the temperature of the mixture, the pressure of the mixture, or increases or decreases the concentration of one of the components in the reaction, you're no longer going to be at equilibrium. So the system, we call it the system, mainly the reaction, is going to want to go back to equilibrium. So they're going to have to counteract that disturbance. So depending on the disturbance, the equilibrium will shift in different directions. So when we talk about Le Chatelier's principle, there's the three main components. There's the concentration change, there's the pressure and volume change, and there's the temperature change. So this talks about the concentration change. So here I have gaseous water going to products of hydrogen gas and oxygen gas. But if I go in the reverse direction, I get gaseous water from hydrogen gas and oxygen gas. So it is at equilibrium here. If I was to change the concentration of any of the gases, the hydrogen, oxygen, or the gaseous water, the system's not going to be at equilibrium. And it's going to have to shift either to the left or the right to achieve that equilibrium balance again. So for example, if the concentration of the hydrogen gas is increased, so I'm increasing the concentration of the hydrogen gas, which way will the system shift to reach equilibrium again? So the way to think about this is that I am taking away hydrogen gas, which means that I'm not at equilibrium anymore. I have less hydrogen gas than I should. In order to gain that hydrogen gas back, I'm going to need to shift to the right in order to increase the hydrogen gas concentration. Now, another way you can think about this is that if I'm decreasing the product, I'm going to have too much reactant. The reaction will be reactant favored. So in order to get that equilibrium, that perfect balance back, I'm going to have to shift to the product side. So if I'm getting rid of hydrogen gas, the system wants to increase the concentration of the hydrogen gas. So it does that by shifting to the right to create more hydrogen gas. The other thing we talk about with Le Chatelier's principle is volume and pressure. Now, this pertains to gaseous systems mainly, but the relationship between volume and pressure is inversely related, meaning if the volume of the container goes up, your pressure is going to go down. They're inversely related. So if the volume of a system is increased, you're going to reduce the pressure. So in order to increase the pressure, the system is going to go to the side with more moles. So when you're looking at volume and pressure relationships, you have two options. Either you're increasing the pressure, which is also reducing the volume. In that case, you're going to go to the side with less moles, meaning you want to raise the volume of what you have, so you're going to go to the side where there's less of it in order to increase the volume. If you decrease the pressure, you're increasing the volume. So you're going to shift to the side with more moles to decrease the volume. Then we have temperature. Now, if you recall, reactions can be endothermic or exothermic. An endothermic reaction, heat is a reactant. It's being absorbed. In an exothermic reaction, heat is a product. It's being released. So in this case, I have a reaction here. Carbon monoxide and water forms carbon dioxide gas and hydrogen gas. Now, if you want to think about heat and you're looking at it with Le Chatelier's principle, sometimes it's helpful to write heat as a reactant or product. And in this case, it's an exothermic reaction because the delta H is negative, so heat's a product. So if the temperature of the above system is decreased, I'm taking away the temperature, which way will the reaction shift to reach equilibrium? Well, if I'm taking away the temperature, right, that means that I'm losing temperature on my product side. So I'm going to need to shift to the right to increase the temperature, because I'm taking away temperature, meaning you could think of heat as a product here. If I was decreasing the concentration of hydrogen gas, I would shift to the right. You're decreasing the heat, so you're shifting to the right to increase the heat again. So that's just one way to think about it. It's helpful to write heat as either a reactant or a product. Okay, so I believe I have two examples here. This really combines everything I've talked about so far. So assume that the following reaction is at equilibrium at 100 degrees Celsius. Okay, so it's methane gas plus water, gaseous water, and I'm getting hydrogen gas and carbon monoxide gas. So notice the delta H here is positive, which means it's an endothermic reaction, which would mean heat is a reactant. It's being absorbed. So just keep that in mind here. Which one of the following changes will cause the reaction to shift to the right? So we're trying to get a reaction that's product favored, shifted to the right. All right, well, let's look at the options here. Decreasing the volume of the container. No. If I decrease the volume of the container, I'm going to want to go to the side with the less number of moles, and that would be the left side. So that would not cause a shift to the right. If I increase the pressure, it's the same thing as decreasing the volume, so that would also be a shift to the left. If I decrease the methane gas concentration, I'm going to want to raise the methane gas concentration. I'm going to go to the left, so that is not it. If I increase the carbon monoxide concentration, I'm going to need to counteract that by getting more reactant. So I would shift to the left. So that is not the answer either. So that means that increasing the temperature should cause a shift to the right, and that's correct. If I increase the temperature, I'm going to have too much heat on this left side because heat's a reactant. It's an endothermic reaction. So to counteract that, I'm going to need to put more heat on the right side. I'm going to shift to the right because if I'm increasing the temperature, there's too much heat on this side, I'm going to shift to the right. So the answer here would be E. Increasing the temperature would cause a shift to the right. Okay, predict the effect the following stresses will have on the following system at equilibrium. So endothermic reaction again here, decomposition of dinitrogen tetraoxide. So I'll put heat here again. Now you don't have to do this, but sometimes when you're just starting to learn Le Chatelier's principle, it is helpful. So, okay, I'll choose a magenta here. So, predict the effects of the following stresses. So, which way will the system go upon these stresses? So, if I add dinitrogen tetraoxide, I'm going to want to lower that concentration, which means I'm going to want to shift to the side without that reactant. So I'm going to shift to the right. So I'm going to indicate an arrow whether it's right or left, but adding more of the reactant is going to cause too much reactant, so I'm going to need to form more products. So I'm going to shift to the right. If I increase the pressure, if I lower the pressure rather, I'm increasing the volume, which means I'm going to need to go to the side with more moles. And here, the side with more moles is the right side, so I'm going to shift to the right. So lowering the pressure is the same thing as increasing the volume. Okay, if I raise the temperature, I'm going to also have to shift to the right because it's an endothermic reaction. So raising the temperature means I have too much heat. I'm going to need to shift to the right. Adding a catalyst, okay, this is interesting. Adding a catalyst actually would have no shift because a catalyst does not affect the equilibrium concentration or expression. It just helps us reach equilibrium faster. So a catalyst will never cause a change in equilibrium. If I'm increasing the volume, that's the same thing as lowering the pressure. So that would be the same thing as B. So that would be a shift to the right. And if I decrease the concentration of NO2, I'm going to want to increase that concentration because now I have too much reactant and I'm lowering the concentration of nitrogen dioxide. So I would also need to shift to the right. So in this case, all the shifts were to the right, but it really depends. So I hope this video helped you to understand Le Chatelier's principle. In future videos, we'll discuss the reaction quotient, K, we'll discuss Q, we'll discuss how to write equilibrium concentration expressions, and we'll do some math.